So we are about to finish with producer theory. We just were looking at Leontief production functions. Let's say a few more words about them. And then I will go back to the Cobb-Douglas functions. So for the Leontief production function, we observe that the demand for input I is AIY. Okay? This is quite clear from every point of view, because if I want to produce I, and I know that I need this amount of input I to produce Y, then the smallest amount I need is this one. So I will use this smallest possible amount, regardless the prices. Prices have no influence. So this demand doesn't depend on prices. If you want to write it with vector format, x of yp is ya, where a is the vector of ai's. Okay? Also, the cost function, we prove it to be ypa. So it's linear in P. Then the Jacobian matrix of the demand function, which is the Hessian matrix of the cost function, has no interest here. It does not depend on P, so the gradient is 0. It's linear on P, so the Hessian is 0. So no information. But what about Cobb-Douglas functions? What is the information we get by applying the results we obtain in general for the differentiable case? So for Cobb-Douglas, the expression for the demand of input I was I'm not sure because I have a different notation here. I think it was alpha j y over a to the power 1 over alpha times 1 over pj As usual, alpha is the sum of the alpha i's. Was this the expression? Do you have the notes to check that this was the expression? Is it okay? Good. Then what is the partial derivative of j with respect to pk? Then I have to take the derivative of this with respect to pk, so only the k factor plays some role. So for this factor, the derivative would be alpha I alpha times pi pk alpha k to the power, sorry, it's alpha k, okay? To the power alpha k divided by alpha times 1 over alpha k. So this is minus 1. Okay, so this minus 1 will make one factor of this type to go to the denominator. So I get, let's see, alpha j alpha k divided by alpha, but this alpha k simplifies with this one, and then, however, I get another alpha k coming from this minus 1. Here I had 1 over pj, and now I have 1 over pk. Is the computation correct? Then we see that it is true that the partial derivative of fj with respect to pk is equal to the partial derivative of xk with respect to xj. But this expression is symmetric in j and k. You have alpha j alpha k, and you have pj pk. The dependence on j in k is only there. Okay, so it's true what we said. Then what about the partial derivative of xj with respect to its own price? So this is true for k from, sorry? I cannot hear you. To pk. What is missing? So this expression is not correct? Ah, yes. Yes, yes, yes. Now it is totally correct? No, what I computed is the partial derivative of xj. Ah, thank you. Now it's totally correct. But even though I don't understand what will happen now. If this is correct, so I'm taking derivatives with respect. Ah, okay. No, now I understand. The point is that when I take the derivative here with respect to Pj, Pj occurs here. So what I get is well, everything which does not depend on P is okay. This is 1 over alpha. And then I have to take the derivative of this product, which gives minus 1 over Pj to the square times the product plus 1 over Pj times the derivative of this, which we have done many times. So is this with j instead of k, so it gives 1 over alpha but then I will get, when taking the derivative of the j factor here, I will get alpha j divided by alpha and this will be dividing thanks to this factor minus 1. So I will get alpha chi divided by alpha, if I am not wrong, alpha j divided by alpha the product well alpha j divided by alpha but also 1 over Pj. Okay? Am I right? Times the product. Is this correct? Pi. Thank you. Is this now correct? Then what I get is alpha j y over alpha to the power 1 over alpha and then alpha j over alpha minus 1 from here times 1 over pj squared times the product. Is this correct? Then this is negative because all factors are positive except this one. Alpha j is smaller than alpha. Alpha is the sum of all the alpha i's which are strictly positive. So this is smaller than 1. With minus 1 it gives negative, so in total it is negative, as we saw. Okay? That when the price of one input increases, the demand for that input decreases, which you said must be the case. It is the case here, but in consumer theory it's not always the case. We gave you several examples that will convince you. So to conclude with this consumer theory, I have to address one important question. To obtain these results on the Jacobian matrix of the demand function, I was assuming differentiability of the cost function. This is not a very nice assumption because the cost function is not a primitive of the problem. The primitive is the production function. Then the natural question is under which conditions on the production function the cost function will be differentiable. And there is an easy result which I am going to show you to conclude this part on producer theory. So suppose, so it's a theorem. Suppose F, our production function, is, which were the regularity assumptions that we found to be natural? Quasi-concavity, non-decreasingness, and upper semi-continuity. Now we will make slightly stronger assumptions, which will be sufficient for the differentiability of the cost function. Instead of quasi-concavity, I will assume strict quasi-concavity. I will define strict quasi-concavity immediately after finishing the statement, but this is a very delicate point because the terminology is not uniform. It keeps changing. Okay? There is a definition of there was a definition of a strictly quasi-concave function, so that a strictly quasi-concave function need not be quasi-concave. Okay? Very easy examples. Then they changed the terminology, but not everybody followed these change. And these somehow pathological class of functions were called semi-strictly quasi-concave. But it was proved that a semi-strictly quasi-concave function, which is upper semi-continuous, is quasi-concave. Okay, and then what was the name given to functions which are both strictly quasi-concave and quasi-concave? They call them explicitly quasi-concave. So the terminology is a bit confusing here, but I'm going to give you soon the definition of strict quasi-concavity. So a strictly quasi-concave, non-decreasing, and now you are expecting me to write upper semi-continuous, but I will not. Instead of that, I will write continuous. I could have written lower semi-continuous, but upper semi-continuous we always have. So lower and upper means continuous. Then for every y in R plus n such that this function is not plus infinity, and for every p in R plus n, so you remember, if a cost function is not identically plus infinity, it is finite valued everywhere. So this is what I am assuming now. Okay? And this happens when I is achievable. This is not a too high output level. There are inputs that are able to produce this output y. Well, then, in such a situation, for every y and every p, then C as a function of the prices is differentiable at P. So C is differentiable everywhere for that particular Y. The proof is quite simple. This function is regular, is more than regular. So then we know that the solution set, the optimal solution set to the cost minimization problem is the superdifferential of this function at P. Well, so I will prove that the superdifferential has just one element. So I take two elements, two different elements, x1, x2, in the superdifferential at P, and I will prove that they are actually the same. So they are, because of the regularity of F, they are solutions to the optimization problem minimizing P of x subject to f of x greater than or equal to y. Both of them are feasible. They are not only feasible but optimal. So we have that well, and of course, as I already mentioned, the subdifferential of a convex function is a closed convex set. In this case, even compact, because it's the interior of the domain, because the domain is the full space. Okay, the same, of course, for the superdifferential of a concave function. So this set is convex. So I take the midpoint in this segment. And then so we have 3 supergradients, but I claim that for each of them, for every subgradient, this constraint is binding. It's satisfied with the equal sign. Oh, but I forgot to give you, I promised to give you the definition of a strict quasi-concavity, but I forget. So I interrupt the proof for a moment, meanwhile you may keep thinking why we have equalities here. So a function is strictly quasi-concave if for every x1, x2 in its domain, which are different and for every lambda strictly between 0 and 1, one has f of 1 minus lambda x1 plus lambda x2 strictly greater than the minimum of f of x1 okay. So is the quasi-concavity inequality, but strictly whenever possible. It is impossible if lambda is either 0 or 1. So I exclude these cases, and it's also impossible if x1 is equal to x2. Okay? The strict inequality in general. So I exclude these possibilities, and then I call this function strictly quasi-convex. Notice that in the excluded cases, we have equality. So quasi-concavity still holds with this definition of a strict quasi-concavity, unlike in the case of semi-strict quasi-concavity, which I'm not going to define because I'm not going to use. Okay? Well, then, do you find any reason why these equalities should hold? The reason is that, pardon? Sorry? No. I mean, forget for the moment the definition of a strict quasi-concavity. So why a subgradient here, supergradient, should satisfy this feasibility condition with equal sign? Suppose for a moment that it's not the case. For instance, that x1, any element in the subdifferential, superdifferential, satisfies this equality strictly. And now take into account that because our function is regular, this set is the optimal solution set to that problem. Okay? Then if this happened, by continuity, I could move from x1 a little bit while still satisfying this inequality to obtain a better solution than the optimal one. Is this clear? I mean, for instance, take x1 minus epsilon p with epsilon small enough. If it is small enough, this would be still greater than y by continuity. But the objective function at this point, which is still feasible, will be the value at the optimal solution we are considering minus epsilon times the square of the norm of p, and p is not 0. So this should be strictly less than p of x1, which is impossible because x1 is optimal for that problem. So the reason for this equality to hold for x1, but also for x2 and also for the convex combination. No? Any element in superdifferential must satisfy this with the equal sign. This is a consequence of continuity. The conclusion is that f of 1/2 x1 plus x2 is equal the minimum of f of x1 and f of x2. This equality is impossible if lambda is different from 0 and 1, and here it is different because it's 1/2, and if x1 is different from x2. So the conclusion is that x1 is equal to x2. This means two supergradients are actually the same. So the superdifferential is a singleton, and this means that the function is differentiable at this point. So it was not a surprise that the cost function, in the case of a Cobb-Douglas production function, was differentiable, because Cobb-Douglas functions are strictly quasi-concave. But it may be a surprise for the Leontief production function, because the Leontief production functions are not strictly quasi-concave. But nevertheless, it's a sufficient condition. Nobody said it's necessary and sufficient. Okay, so even if that sufficient condition doesn't hold in the Leontief case, but still we obtain a differentiable cost function. And I think I have nothing else to say about producer theory. We have produced already too much. Now the money we earn by producing some output, we are going to spend by consuming goods. Okay? So for this reason, I gave production theory before consuming. So was everything clear? Yes? No question about producer theory? So let's move to please. You are asking about this? So, I mean, according to strict quasi-concavity, this should be strictly greater than if lambda is between 0 and 1, and the lambda there is 1/2, and if x1 is different from x2. We don't have this inequality, strict inequality here. We have equality. This is only possible if this condition does not hold. So x1 must be equal to x2. So two arbitrary supergradients are the same. There is only one. Okay, and this means differentiability. Okay. Any other question or comment? At a point where if it is identically plus infinity, no, if it is plus infinity at one point, it is identically plus infinity. Then you cannot consider differentiability of the constant function plus infinity. Differentiability, as far as I know, is for finite valued functions. It doesn't make sense. Okay. Any other question or comment? If not, we move to consumer theory, a completely different world, but with some similarities in the mathematical treatment. We will see again the crucial role of quasi-convexity and quasi-concavity there. It's not that we define quasi-convex because we like it, because we want to write a paper. No, it's because we find it. We are forced to introduce the notion of quasi-convex and the notion of quasi-concave. As we were forced in production theory, we will be forced in consumer theory again, as you are going to see very soon. So in this consumer world, there are n goods available. And different types of goods. And the consumption space, or the consumption set, is R plus n. Its elements, x1, xn, are commodity bundles. This commodity bundle contains x1 unit of good 1, x2 units of good 2, etc. And we consumers have preferences over such bundles. If I offer you this bundle and this bundle, you will choose one according to your preferences. So your preferences are described by a so-called total preorder. This is the assumption. Okay? So that, saying that this condition holds means that you prefer x to y, or you are indifferent between x and y. So it's preferred or indifferent to. Okay? By preorder, I mean reflexive and transitive. But not antisymmetric. With antisymmetry, it would be an order. So we allow for indifferences. I ask you to choose between this and that, and you say, give me whatever you want, because for me they are the same, although they are different. Okay, by total, economists prefer to use the word complete, which is misleading because a complete ordering in mathematics is something else. So I adhere to the mathematical terminology. By total, as opposite to partial, we mean that for every xy in the space, either, we have x preferred or indifferent to y, or y preferred or indifferent to x, or both. This means you can always compare two commodity bundles. Okay? So these are the only conditions we are going to use. Then in this situation, when you have x preferred to y and y preferred to x, we will say that they are indifferent, or we are indifferent about them, and we will write x indifferent to y. I can also write x strictly preferred to y when x is preferred to y, but y is not preferred to x, so they are not indifferent. And of course, you can also consider the reverse preorder strict or non-strict. These notations are obvious. I think I don't need to explain. Okay? Then, but this situation is too abstract for practical purposes. We are optimizers. We want to solve optimization problems. And optimization problems are described by functions. You don't see any function so far. So we are going to introduce functions, so-called utility functions. So in some cases, your preferences may be represented by a function. Then it is called a utility function representing your preorder. What is a utility function? So u, a function from r plus n into r, is said to be a utility function for this total preorder, or representing this total preorder, if the following equivalence holds true. Whenever x is preferred to y, then u of x is greater than to u of y, and vice versa. Okay, then U represents your preferences. Okay, so if you give me your utility function, I know your preferences. So if you say U of x is 1 and U of y is 3, I know that you prefer y to x. And if you tell me that U of z is 3 millions, I know, I'm quite sure that you prefer z to y. But this doesn't mean that you strongly prefer z much more than y, than you prefer y with respect to x. The numbers do not mean anything, only the relation between the numbers. So what is only important is whether U of x is greater than or equal to U of y or not. The difference between the values does not play any role, because if U is a utility function and h from R to R is a strictly increasing function, then the composition of h with U is also a utility function for the same preferences. Utility function for the same preferences. If you apply h to both sides of these inequalities, you get h composed with U of x greater than or equal to h composed with U of y. And because h is strictly increasing, if h composed of U of x is greater than or equal to h composed of U of y, you get U of x greater than or equal to U of y. So they both represent the same preferences. So I can easily construct you an h such that for this h composed with U at x will be minus 1 million, h composed with U at y will be 0, and h composed with U at z will be 10 to the power minus 6. They also represent the same utility functions for these three goods. And you see here the difference between y and z was huge, unlike the difference between x and y. Here the difference between x and y is huge, and the difference between y and z is very small. So a utility function does not have any economic meaning. It's just a mathematical tool to represent the preferences. It's just something that is very convenient to us because we are used to deal with functions. And we are able to solve some optimization problems which are defined by functions. Okay? So this is an important observation. But now, when does such a utility representation exist? Any total preorder admits a utility representation? The answer is no, but very often yes. A very important result by Gerard Debreu Have you ever heard about this name? I met him once in Paris. He passed away long ago. Gerard Debré was a French and mathematician, working in the United States as an economist. And he got the Nobel Prize in economics. There is the famous Arrow Debré. Arrow was another Nobel laureate. And I also met him in Barcelona, together with other people. We were having dinner together. These are the only, not the only Nobel Prizes I have met. I didn't interact with him, but a very famous Nobel laureate, Indian Nobel laureate in economics, gave a lecture in my department. Can you guess which one? I don't think that, no, there are more than one Indian economic Nobel laureates in economics. Who? Amartya Sen. Sorry? Yeah, this is the one of which I'm reading now a book, a joint book with his wife, Esther Duflo, who is a French economist. And I'm reading a book by them titled Poor Economy. It's about the economics of poverty. Very interesting. Well, but this theorem was produced. So you know, you can be a mathematician and win the Nobel Prize in economics. I failed so far. No, but there are other prizes. There is the Abel Prize. There is the Fields Medal. No chance. Okay. Then he says, suppose we have a binary relation. On R plus n. In fact, this result can be extended to other spaces, and there is a huge literature on extensions of this result to the most exotic spaces you can imagine. And but there is one crucial condition here. I mean, we are going to give a statement about representability of this relation by a utility function. And in general, representability fails. I will give you an example after this statement. So the crucial assumption in the Debré's result is that the preorder, or the binary relation, is continuous. What does it mean? That if you have relations, xk related to yk, and k goes to infinity, they converge to x and y, then in the limit, the same inequality, the same relation holds true. In other words, this being continuous means that the graph of the relation, which is defined as the set of pairs xy such that x is preferred to y. I will not say all the time preferred or indifferent to preferred. If sometimes I consider a strict preference, I will say strictly preferred. Okay, so that this set is closed. Then, his fantastic result is that this binary relation is a continuous total preorder. If and only if it admits a continuous utility representation. There exists U from R plus N into R, continuous, such that U represents the relation such that x greater than or prefer to y if and only if U of x is greater than or equal to y for every xy. Okay. By the way, I said that I am reading a book by this Nobel laureate, and I am reading another book by the other Nobel laureate, Amartya Sen. It's Home in the World. It's a sort of autobiography, very interesting too. I'm like learning about India and about Indian people. I have read a lot of books of all types about India, but I still need to learn a lot. Well, very nice result, not easy to prove, except the implication from right to left, which is immediate. If x is preferred to, if x is related to y, I cannot say preferred because for the moment I have a binary relation. X is related to x because U of x is greater than or equal to U of x, so it's symmetric. If x is related to y and y is related to z, then U of x is greater than or equal to U of y, while U of y is greater than or equal to U of z. And by transitivity of the ordering in the reals, U of x is greater than or equal to U of z, so x is related to z. So we have a preorder, and it is total, but given two elements in the space, either U of x is greater than or equal to U of y, or y of U of y is greater than or equal to U of x, or both. Then either x is related to y or y is related to x, or both. Okay, so it's quite clear. That part is trivial. And continuity is trivial too, because I'm proving the trivial implication, because under this assumption the graph of the relation is the set of pairs such that U of x is greater than or equal to U of y, because this is the same as saying x preferred to y. And that set is obviously closed if U is continuous. I will not try to prove the opposite implication. Okay? But believe me, it is true. Don't believe me, believe the brief. Okay? And a comment. The fact that U is a utility representation, even without continuity, tells me that it is a total preorder. So continuity, when I add continuity, I get a continuous total preorder, but I cannot separate, because if I remove the continuity assumption here, I don't have a utility representation. Cannot be continuous if it is not continuous, but even discontinuous. there may be not utility representation at all. You want to see an example? You know, have you ever heard about a total order relation which is not representable by any utility function? You are going to see it immediately. If we still have time. No? Then again, it's the right moment to interrupt because everybody is very excited about finding such a counterexample, and now, so tomorrow you will be here, I am sure. Okay. Okay, so let's stop here. But okay, I want you to sleep tonight, so I will tell you, I will not make you the proof, but I will tell you the solution. It's the lexicographical order. You know the lexicographical order. How are words ordered in a dictionary? You first look at the first letter. If the first letter comes first, then the word comes first. If the first letter coincides, then you look at the second letter, and so on and so forth. This is the lexicographical order. This is the reason why there is this name. Okay, because it's related to words. I will tell you a lot tomorrow about the lexicographical order. I hope you will like it, the lexicographical order, and you will treat it well, the lexicographical order, because it is very often mistreated. Is exhibited as a monster. Okay, and maybe after I tell you the example tomorrow, you will agree that it is a monster, but it is not. It's just the opposite. So I will try to convince you of both. Not that it is a monster, because it is not, but because simply it does not admit a utility representation. But then I will try to convince you that it's the best, in a sense. Okay? And then you will treat him or her, it, well. Okay? You will never say it's a monster. Okay, thank you. We stop here.